Imitating organisms' characteristics logically leads to the concept of the fittest, which is defined as the ability to survive and reproduce in a specific environment. Evolution occurs in a landscape shaped by fitness and adaptation. An adaptive landscape is similar to function optimization for engineers and mathematicians. Evolution progresses without an explicit purpose but appears intentional. Selection eliminates less fit organisms. Variation and selection navigate the landscape and result in outcomes that enhance survival. Evolution abstracts a landscape composed of alternative genotypes. Organisms exist in a constant state of anticipating their environment. Predictions are associated with reduced surprise. Genetic constitution can link traits such as deafness and fur color in cats. Fitness is influenced by the environment and by other organisms. Mimicry functions as a temporal aspect of an organism's world. Mimicking a bee can provide advantages when other bees are present. The objective function becomes complex when learning from dynamic data, such as in the control of nonlinear systems. The cart pole system is an example of a dynamic learning challenge. Learning in control systems becomes harder when the system shows purposeful behavior, as in gaming scenarios. Evolutionary algorithms can model participants in games. Mitigating premature convergence involves introducing new randomized populations using heuristics such as hill climbing or applying re-engineering approaches. Early literature on evolutionary algorithms often favored high crossover rates, which increased the risk of premature convergence. Repeated premature convergence suggests the need to reassess and modify variation operators. Representation in evolutionary optimization requires careful choices regarding representation, selection, and variation operators. Binary string representation was once common, but is not suitable for all problems. Real-valued encodings challenge the building block hypothesis in genetic algorithms. Mutation rather than crossover proves successful with real-valued representation, leading to real-valued genetic algorithms. Selection methods such as plus comma, proportional tournament, and linear ranking affect parent survival and offspring generation. Proportional selection chooses parents based on relative fitness. Some binary encodings proposed for complex problems did not outperform alternative methods. Designing optimal schedules for a bus company involves constraints such as limited buses, budget, drivers, and vehicle capabilities. Evolutionary algorithms must address both hard and soft constraints. For example, golf club design must follow strict length constraints. Balancing mutation step size and progress rate is essential for success. Meta-evolution in evolutionary algorithms involves adapting parameters during the search process. Self-adaptation can be used to regulate variation operators and their probabilities. And this is important for evolutionary optimization across different scenarios. Static configurations for variation operators may not remain effective because their usefulness changes during evolution. Self-adaptive meta-evolution can combine different operators to improve performance. The fitness distributions of variation operators are also important considerations. Applying a variation operator to one parent or a group of parents produces offspring according to a probability distribution. Choosing different variation operators or adjusting their parameters changes the likelihood of sampling points across the solution space. Evolutionary algorithms are a family of computational methods inspired by the principles of biological evolution. They are designed to solve complex optimization and search problems by mimicking natural processes such as selection, mutation, recombination, and survival of the fittest. Instead of trying to directly calculate the perfect solution, evolutionary algorithms generate a population of possible solutions and improve them gradually over time through an iterative process. At the core of evolutionary algorithms is the idea of a population. Each individual in the population represents a potential solution to a problem. This solution is encoded in a specific format, which may be a binary string, a real valued vector, or another structured representation, depending on the nature of the task. The quality of each individual is evaluated using a fitness function. The fitness function measures how well a given solution performs with respect to the objective of the problem. Solutions with higher fitness are considered more successful. The evolutionary process begins with an initial population that is usually generated randomly. Each individual is evaluated, and based on fitness values, certain individuals are selected to produce offspring. Selection is a crucial mechanism because it determines which solutions are allowed to pass their characteristics to the next generation. Common selection strategies include proportional selection, tournament selection, and ranking methods. These approaches balance exploration of new areas in the search space with exploitation of promising solutions. Variation operators are then applied to the selected individuals to create new offspring. The two most common operators are mutation and crossover. Mutation introduces small random changes into an individual, allowing the algorithm to explore new regions of the solution space. Crossover combines parts of two or more parent solutions to produce new offspring, potentially inheriting the strengths of each parent. The balance between mutation and crossover strongly influences the behavior of the algorithm. After offspring are generated, they are evaluated using the same fitness function. A new population is formed by replacing some or all of the previous generation. This process of selection, variation, and replacement repeats over many generations. Over time, the population tends to improve as more fit individuals dominate the search space. However, maintaining diversity is important to prevent premature convergence, which occurs when the population becomes too similar and gets stuck in a local optimum. Evolutionary algorithms are particularly useful for problems where the search space is large, complex, nonlinear, or poorly understood. They do not require gradient information or strict mathematical properties of the objective function. This makes them suitable for engineering design, scheduling, machine learning, robotics, financial modeling, and many other fields. For example, they can optimize control parameters in dynamic systems, design efficient networks, or evolve strategies in competitive environments. Several well-known types of evolutionary algorithms exist. Genetic algorithms focus on binary or real-valued representations and emphasize crossover. Evolution strategies emphasize mutation and self-adaptation of parameters. Genetic programming evolves computer programs or symbolic expressions. Differential evolution specializes in real-valued optimization problems and uses vector-based mutation strategies. Although these methods differ in implementation details, they share the same evolutionary principles. A key strength of evolutionary algorithms is their flexibility. They can handle multiple objectives, constraints, noisy evaluations, and dynamic environments. Advanced approaches incorporate self-adaptation, where parameters such as mutation rate evolve alongside the solutions. This meta-evolutionary process allows the algorithm to adjust its own behavior during the search. In summary, evolutionary algorithms are powerful and adaptive optimization techniques inspired by natural evolution. By maintaining a population of solutions and applying selection and variation over successive generations, they are able to explore complex search spaces and find high-quality solutions, even in challenging and uncertain environments.